the debate that's about to happen very shortly. But before that, I'd like to talk a little bit about debate in the health sciences and what we do and what we want to do. So I think the goal of debate in sciences and health is twofold. First of all, we want to have discourse about breakthrough issues in science and medical ethics, and we want to get students, or Cornell students specifically, engaged in these issues, talking about ethics, talking about new breakthroughs in science, and how it relates to them. The second goal that we have is about reaching out to the greater Ithaca community and Cornell community and sparking discourse about key issues that affect their day-to-day lives, whether it be about vaccines and how important they are and about how the ill effects might not be as great as some people advertise, or whether it be about things like CRISPR, which affects the scientific community and researchers. So if you guys are interested in doing this sort of stuff and doing outreach or just talking about these sorts of issues, please come up here and sign your net ID so we can put you on our listserv and send you emails in the future about the sorts of event that we do. So I think before we start this debate, we're going to have a short talk about CRISPR-Cas9 and some basic context from Dr. Sarvari. He's the Senior Director of the Cornell Investigative Laboratories, and he's quite knowledgeable of the field. So without further ado, I'd like to welcome Dr. Sarvari.
And modifying the human genome for a very, very long time. So since the 1920s, Frankenstein movies through more recent Game of Thrones episodes, you can see that modifying the genome is something that's always in people's mind, just because it's fighting natural selection, it's fighting evolution. And technically, this is where we are heading. We want to create superheroes. We want to be superheroes. And the way what our power is going to be as superheroes is to live longer, live healthier, be more resistant, and survive. Right? So get all that natural selection and evolution and mutations driving evolution craziness that I teach in aside, and try to get over that and be stronger, be faster, be better in survival. So that wasn't really a case. You couldn't really do that until very recently when news like this came out. This is just from 2015, when we are finally getting to the point we scientists, we humans, can modify the human genome. And not just poke it and try to play with it a little bit, but really getting that superhero power that we are seeking, and we have been seeking for quite a long time. And I don't think, lots of people say scientists are playing God. I don't think that's the case. I like the superhero reference a little bit better, just because it is something that we want to evolve with in sort of an artificial way, but we want to include that in our evolution. And CRISPR and CRISPR-Cas system, when it was found, it really opened up a new door to molecular biology, and especially DNA editing and gene editing. So this is something that you all see in biology courses. With DNA replication, we have a really good mechanism, and all cells alive have a really good mechanism for replicating DNA. And by replicating DNA, meaning that the DNA polymerase is not only able to assist that process, but also able to find errors and correct them immediately. And when DNA polymerase fails, we have mutations, and through those mutations, we can evolve, and we have been evolving throughout millions of years. And this is the whole idea. After DNA replication, through transcription, you are going to create an RNA, and through translation, you are going to create a protein. And that protein can be an enzyme, that protein can be something that will be phenotypically expressed, and we are going to be able to observe. And also that's the protein, that's the phenotype that natural selection applies to and select for or against. Now how does it fit into the CRISPR-Cas9 system? It was found that even bacteria have an immune system, which is really surprising because bacteria are not really the smartest creatures on this planet, but they are able to remember bacteriophage, which are viruses attacking these bacteria, and the way they remember it is by copying a portion of their DNA. You know, viruses are just pieces of DNA. They don't even have the cell walls or cell membranes. And the bacteria, if it survives, the bacteriophage, is able to copy these short, around 20 base pair long DNA sequences and store it in an RNA. And they just have this memory, so next time they are being attacked by this bacteriophage, by this virus, they can respond much faster. And they can use endonucleases, which are proteins or enzymes, to cut this foreign DNA, cut this virus, and the bacteria can protect themselves through this very primitive immune system. So why is this important? Because the RNA, and in this case we call it the CRISPR RNA, is really just guiding this endonuclease, this enzyme, to the spot where it should be cutting. And where it cleaves the foreign DNA, the DNA from the virus, at a certain specific spot. So the idea was, based on this immune system of the bacteria, what if we can design RNA, which scientists, molecular biologists have been doing for decades. We can design specific RNA which can lead this nuclease or any sort of other enzymes to this spot to cut the DNA. And this is where CRISPR and CRISPR-associated genes, the Cas genes, come into play, because they are the ones that code for this Cas9 system. That's the enzyme itself that can cut the DNA. So this is how we can apply this in DNA editing and modern molecular biology. We can program this RNA, which is an RNA guide, it will lead us, or it can find actually a certain DNA fragment that we are interested in editing among all the millions of base pairs and DNA sequences. It will be able to locate that certain one that we need. It can bring the Cas9 enzyme, this endonuclease, to the certain spot where it's able to cleave or cut this DNA. And when this DNA goes through the entire DNA replication process I showed you earlier, it will go through and repeat itself over and over and over. Also, the DNA polymerase is able to either insert other DNA fragments or delete DNA fragments from this DNA sequence. So we can target our DNA, and also we can cut it at a very precise place, and we are able to insert or delete parts of this DNA at that spot. So it became sort of a surgical procedure that used to be this very non-specific process. So you can imagine that it's almost like attacking a piece of paper with a pair of scissors, or going there and trying to cut up a piece of paper with an axe. Right? So the spot where you are going to cut your DNA is much more specific with this CRISPR-Cas system. So where it comes into play, it's not just cutting that piece of DNA, but also, as I mentioned earlier, either repress that or inhibit that part of the DNA that we are not interested in, or getting a piece of that DNA activated so it starts to code for that required RNA and then protein. And of course, as you will hear it in the debate, because this is a process that narrowed down how long it takes us to edit DNA, made it really, really cheap. Right now it's so cheap that we are actually thinking about in the investigative biolabs to develop a module that you as students can come in and use this system, because it's very affordable and very quick, so even in one semester you can learn it quite a bit. That wasn't the case. A couple of years ago, we wouldn't have been able to do this. And now this system is in our hands, and we can use it. And therefore, people are using it. And using it to start to get that superpower that I was mentioning earlier. And I'm not going to mention any more about that because that's part of the debate, but it's also an issue regarding who owns this system, who found this system first, and who can apply. So I don't know if the debate is going to discuss that, but Jennifer Doudna is the one at UC Berkeley who first described this system, but since then many other scientists claimed it and have been developing it further. So that was my short introduction. I hope it gave you enough information about the system that even if you are not familiar with CRISPR and Cas9, that will help you understand the debate and help you start to think about the ethical use of this modern molecular biology. Thank you.
I think we're going to go ahead and get started with the debate then. A little bit about the format. So Patrick and Alex, who will meet shortly, will be promoting the motion, and Richard and Mario will be opposing that. And the topic that we're officially debating today is human gene editing ethical? And there will be 5-minute speeches, and let's get started with the debate then. Patrick, what do you want to do? Just as a reminder before Patrick starts speaking, the positions held by the debaters here today aren't their own positions. It's just a random assignment of the topic that they were given to debate. Yeah.
Thank you, Swan. So I'm Patrick. I've been part of this club for 4 semesters, and I invite you to speak with me or anyone after the club to ask questions or anything you'd like afterwards. So, as Swan said, the crux of this debate is asking whether or not human gene editing is ethical. And I think really what I want to impart to you at the end of the speech is that it's ethical because the costs of not doing so are too high. There's just too much potential with this technology to improve human health and even save lives, but not doing so is foolish and ultimately unethical to do. So why is this a question now? As Dr. Sargary said, we now have in our possession the ability to essentially, to essentially cut the genome and insert things with specificity. And that's remarkable, and that means that many genetic disorders and diseases that previously might have been a problem now are much less so, because now we have the ability to just target that gene or target that disease and even do research into that disease much more effectively. In the past, numerous countries such as Canada, France, Germany, South Korea, and quite some time ago ruled that human genetic engineering is illegal to do in their country. And certain countries such as the US are very hesitant to give funding for any projects that actively explore human genetic engineering of either human embryos or just human cells. So what we're doing is we're supporting the ethics and supporting the fact that we should be promoting genetic engineering on human cell lines. And that's really for 2 reasons. First, because of the powerful benefits that it provides to research and to researchers looking to cure human diseases. And then secondly, in the ability to actually cure the diseases themselves. So I'm going to draw up some few examples to kind of highlight why I think these are important points. So first, let's look at an example of what Chinese researchers did quite recently. In January of 2016, this was published in Nature. What these researchers did is they took human cells that had been diagnosed for a likelihood to develop autism. They compared these cells to normal human cells which hadn't had this likelihood to develop autism, and they saw it was different. This we could all do before. However, what they did that was unique with the new invention of CRISPR-Cas9 is that after isolating the fragments that were different, they then cut them out, took good care of them, and then put them into monkey embryos. And these monkeys have very similar genes, of course, to ourselves, like a 99.99% similarity. And then when those monkeys grew up and those monkeys basically started to exhibit signs of behavior, they noticed that the monkeys with certain genes in them had different behavior that they attributed to autism. And essentially the result of this is that they identified an overexpression, or basically an over-duplication of something called the MECP2 gene, to be potentially attributable to the ability to gain autism. So I don't want to get too technical with this, but I think it's easy to understand how even allowing ourselves to embrace the fact that human genetic engineering has some potentially good consequences vastly, immediately accelerates our understanding of human diseases in some field. Because the genetic components of autism or other components such as vaccines were debatable about whether or not this is the cause, and if so, what specific genes are the cause. But what CRISPR-Cas9 has allowed us to do is, with the flexibility to operate on human cells, vastly increase our ability to potentially treat and diagnose autism in the future. However, let's look at kind of the sexier side of the issue. It's actually treating people who are immediately going to get this disease. So I want to look at two examples, both kind of preventative care of an embryo that might develop a disease, and actual care of a person who's been diagnosed with this disease now, how can we help them? So first let's look at immediate care. Again, I'm going to draw an example of a 1-year-old with leukemia. This was reported on by the Huffington Post on November 5th of 2015. The situation was a 1-year-old was diagnosed with critical leukemia. Basically, they tried everything, it hadn't worked. It was like straight out of house MD. However, what they did have as kind of a last resort was an experimental drug developed by a different British pharmaceutical company whose name I can't pronounce and I forgot to write on my paper, sorry. But a different pharmaceutical company that basically had this drug that they had experimented on by modifying human immune cells, because leukemia is essentially cancer of the blood. So it's your blood cells are being attacked, so your blood no longer works. So what they did is they put these modified immune cells, which no longer had, and these cells were modified with CRISPR-Cas9, of course, that's why I'm mentioning them. They put them and they just basically did a huge overhaul of the 1-year-old's blood and inserted these new cells instead. And what they found is that this 1-year-old was actually cured. Kind of the legal ethics of this were contingent on the parents agreeing to this last-minute procedure. But what it's done is it's basically showed that CRISPR-Cas9 research can have immediate benefits to human health. These were cells modified by CRISPR-Cas9. It was a highly experimental procedure. But of course, the British pharmaceutical company that, happened to have this drug in their, kind of concocting in their experimental laboratories, they're now ramping up the production. And the hope is that the United Kingdom will loosen the restrictions on human genetic engineering funding so that these kind of treatments can become more commonplace. As we see again, this has the potential to save lives. So the longer we debate its ethics instead of acting and convincing countries that they should support these kind of endeavors, the more benefits we can bring. However, let's look at another example of preventing diseases before they even happen, before this 1-year-old gets leukemia. The idea is most attractive with Mendelian diseases, which are diseases of a single gene. And what this means is essentially, this would be a disease like Huntington's or Parkinson's, which are diseases that are essentially mostly caused by sometimes even a single codon changing within a gene. So you can identify a single gene that's causing a misfolded protein, for instance. That is the cause. If you were to fix that gene, that would be the cure. And that's the motivation actually behind the human embryo experimentation that Dr. Sarvari showed. We want to be able to isolate embryos, and we've had the ability to diagnose them before. But now what we would be able to do is say, wow, this embryo has a high chance of developing this mutation. Let's just implant the gene from a healthy embryo into this unhealthy embryo. And then all of a sudden, without recycling embryos, without causing loss of potential human life, you've cured Huntington's in that animal, in that human. And research has been done to show this is true, and the example that I'd like to draw on was published in Science on October 20th, 2015, when once again, I think it was Chinese researchers once again, did this experiment on mice, and they found that mice who have Huntington's as well were completely cured of disease whenever they simply identified the gene and fixed it. So what really do I want to emphasize upon you today? I want to emphasize that by supporting human gene editing, by agreeing on its ethics, we essentially get a result. So if we don't pursue human gene editing and we don't support its efficacy, we might have some risks and some consequences. But the thing is, now with the advent of CRISPR-Cas9, the risks of not doing so are much greater than the risks of doing so. Before, many countries ruled it as illegal because they're worried about the controversy and the potential risk to human health. But now what we can see is that the risks of not doing so involve the cost of numerous lives and overall the health of people who are involved in or who may have genetic diseases. So, thank you.
Patrick, for that speech, and I invite Richard to open up the opposition.
So my name is Richard. I'm a junior in human development, and I just wanted to thank all of you for coming here because I think the kind of things that we do here at DSH, workshops, debates, will really be useful for any of you who are interested in terms of your careers, especially if you're interested in things like scientific research, medicine, policy, things that involve saying words. So I think this will be a good debate. So me and Mario, my partner Mario, are on the opposition side. So we are totally against the idea of using gene editing, using genetic modification to edit the genomes of humans, at least at this point in time. We totally agree with Patrick that biotechnology's major breakthroughs like CRISPR are really important, really significant events. But what we don't agree with is about the ethics of it, whether or not it is ethical to have such a powerful technology be basically released into the public at this point in time. Because what Patrick and Alex are telling you on the proposition side is that they're promising you this big promise, giving you the ability to drastically and permanently increase our control and stranglehold over human biology, which in the future could very well lead to a very widespread public access to manipulating the human genetic makeup. And what Patrick wants to do is basically to pursue, to fund, and to distribute technologies like CRISPR-Cas9 as rigorously as possible in order to save lives. And me and Mario agree that saving lives is really important. And we might even agree that using genetic editing is permissible ethically, just not right now. And the reason why is just because the technology is so new that there's just way too much uncertainty about the biological effects, about regulating abuse, that we just think that the only ethical path, at least right now, is to put a moratorium, a temporary stop on uses of human genetic modification, at least until we've researched the effects more. Alright, so what are we going to be arguing on the opposition? I'm mostly going to be arguing about the biological risks, the technological risks, whereas my partner Mario is going to talk about more of the socioeconomic risks, the risks for abuse. Okay. So what does Patrick say during his speech? He claims that genetic modification is really beneficial and vital to curing two types of diseases. The first kind are monogenic diseases. These are diseases like Huntington's, where you basically just have to change the allele for one gene in order to prevent the disease from expressing itself. The thing is, though, for monogenic diseases, it's actually very unnecessary to invade an embryo that has the disease and to edit the genes. Actually, what you could do is just take a bunch of the embryos and just pick out the ones that are likely to express the genes. And they might say, well, what if you have a dominant disease or a homozygous recessive disease where both alleles are recessive, so it'll express disease? Well, those diseases are extremely rare. Diseases like Huntington's, which are the ones that Patrick talked about, aren't those kinds of diseases. The second kind of disease are polygenic diseases, and the argument behind this one is quite simple, which is that there are some diseases, very common ones like cancer, like heart disease, which are influenced by literally hundreds of thousands of genes. And so it's not as simple as Patrick makes it out to seem, where you just flip a few switches and boom, you've cured a disease. For something as big and complicated as cancer, it's almost impossible to fathom, at least at this point in time, that we can use gene editing to just get rid of those kinds of diseases. And that leads on to the next argument. Because given the amount of uncertainty about the benefits, we think that the amount of risk involved, which is mainly due to the uncertainty of this new technology, we just don't think it's worth it. Those kinds of errors could mean inaccurate editing, incomplete editing, or even unintentionally creating phenotypes that we didn't even know about. A very good example is the E4 variant of the ApoE gene. Basically, this gene is highly correlated with causing Alzheimer's disease, which we would all agree is a very bad thing. The thing is, though, is that this allele is also correlated with working memory in young adults. And so my point here is that this is just one example of how genes don't just code for a single bad thing like a disease, but also code for other things which we might need, and which might unintentionally be harmed if we go into genetic modification. Our point on opposition is basically just that human beings are really, really bad, at predicting the consequences of even small changes to things like our own biology, to our own genes. And what this technology does is that on a widespread scale, it gives us access to edit the entire genome. And what my partner Mario is going to talk about is how that's likely to be abused, how it's very unlikely that will be regulated well, and of course, how that will also create social inequality.
Thank Richard for that speech, and welcome Alex to continue the proposition, please.
So on the government side, we proved to you or shown you in various different ways in which this technology has potential to save lives, while the other side is proclaiming this nebulous picture of potential incalculable risks, in which it's impossible to really understand the way in which the delays in which this technology could wind up destroying the potential for research that could yield important results for the treatment of disease. Richard's speech brought you 2 points. They say that there's hundreds of thousands of disease, there's hundreds of thousands of genes, and it's impossible for us to know the extent to which our actions could have an effect on the human genome. We say, great, there's thousands of genes that we have to look at. Let's start now and ensure that we're able to get the research done to understand the ways in which genes are expressed. But second, the way they talk about genes being complex and cause unnecessary harm, we think that you only are able to get the kind of results we're able to understand the human genome when you wind up having exploratory research, having the Bruce Waynes of the world pay for their son to be super strong, by making sure that this technology is engaged upon, that we're not necessarily stuck in this precautionary stage and we go into ensuring that exploration into the human genome happens and happens to a significant extent to which we're able to get the kind of results that research necessitates when there's thousands of people suffering from diseases that could be cured under a government policy. So what does this debate come down to? Exploration versus precaution. The other side is claiming that the idea of this unknown risk has stopped exploration into this technology altogether. We did not know what kind of diseases astronauts could have developed when they went to the moon, but of course they went to the moon anyway, not because it was easy, but because it was hard. The fact remains there's always some degree of incalculable risk for deploying new technologies to delay life-saving treatment because we do not know what lies beyond. It is foolish and inhumane considering the amount of lives that are on the line in this debate. We've seen the impact of this thinking in debates about GMO crops and novel foods and greenhouse gases. At every stage, the opponents of technological progress argue that because there's no evidence of harm, it doesn't mean that something's not harmful. So the thing is, just because someone says that there's fairies in the garden doesn't necessarily mean that you have to have actually seen fairies for those fairies not to be there. So at the end of the day, look, this is a technology that has the potential to target genes outside the genome to cure cancerous cells. Right now, the ability to target these cells is in its infancy stage, but in order to understand how to target genes mutating disease to the epigenome or the genome requires significant research funding from private actors. It needs results, and government policy that makes this more difficult by limiting its use ensures that finding this funding is more difficult. So what lies beyond? What are the potential risks? Every mutation that occurs the fact of the matter is there's an estimated 170,000 people in the U.S. expected to be diagnosed with leukemia, lymphoma, and melanoma in 2016, and by not a death sentence, these kind of diseases have a 62% survival rate. We think it's important to prioritize these individuals versus prioritizing the unknowns which they've identified. We don't believe that the extent to which these technologies could be hindered, the research that we possibly are going to develop will ensure that these individuals are able to live a better life. We're not really sure what lies beyond, but it's important that we go ahead with this kind of research. It can make a significant change in people's lives and can ensure that individuals who have these diseases could wind up living a long and fulfilling lives. I'm sure that individuals would gladly avoid Huntington's disease and leukemia if it meant that they could possibly alter their genome. We think that these kind of things have such a significant effect on people's lives that we're willing to bite the harm that individuals might have some potential unknown damage to their genome if at the end of the day they're able to live long and fulfilling lives without some of the external factors limiting their productivity or limiting their ability to live a long, productive life. So why does class also not matter in this debate, and why does our side at the end of the day get better accessibility for everyone? We solve for the 99% and to a large extent by overcharging the 1%. We're not really looking at a zero-sum game in this debate, because we believe this technology is in its development stages, and more research is required to ensure this technology is available cheaply and affordably to more people. At one point, computers, televisions, radios, and cars were confined in ownership to the wealthy classes, but over time, the potential that private actors had to reduce the cost and make these things available to a mass market encouraged Henry Ford to come up with the assembly line and Bill Gates to come up with the personal computer. These kind of private incentives existing in the private sector will ensure that there's incentives along the lines for mass market availability of these products that were once seen as luxury goods. We're fine with ensuring that like rich individuals pay like private large amounts of songs, their arms and limbs, to be able to ensure that this research takes place, and without having these private actors involved, without enabling these services to be available to individuals, we're not able to grasp that large amount of private funding and ensure that more individuals are going to be able to get treated in the long run. 50 years into the future, we have to decide whether or not this technology has the potential to save thousands of lives. And we feel that 50 years from now, the technology will be much farther along the line to addressing the 170,000 cases of leukemia and lymphoma than a world in which we didn't go ahead with this technology. And the type of research in progress is not available because we never let it happen in the first place. So we are very proud to propose and ensure that every family at the end of the day is going to get access to a technology that can save their child's life. We are proud to propose. Thank you very much.
And welcome Mario to continue the opposition case and close off the debate as a whole.
Right, so I'm Mario. I'll be closing out this debate. Can you all hear me in the back? Okay? Awesome. Right, so, yeah, my opponents here would assert that genetic. I will start the timer. Right. So, my opponents would assert that genetic engineering does not come at any cost, and that this should be distributed for wide use overall. However, this is patently false. And you've actually already seen this evidence in this debate. As my colleague Richard has already mentioned, the ApoE gene, for instance, has plenty of evidence behind it stating that if we delete this gene, ApoE, by the way, is a gene that affects the formation of certain lipoproteins in your body, carriers of fats in your body. If you delete this gene, we would decrease the risk of cardiovascular disease and even decrease the risk of Alzheimer's. However, there's also evidence that states that that this gene is associated with better working memory results. In other words, better short-term memory. So obviously, genes like this have a sort of pro and a con. They are complicated and they interact widely with one another. We have only begun to look at the genome. The Human Genome Project was only completed in 2003, and we are barely starting to understand all the complex interactions between all of the myriad of genes, myriad of alleles that could possibly happen. And thus, we, the opposition, would state that we simply do not know enough about these interconnections and about the consequences of editing the human genome to state that this is actually, truly an ethical option to have. This isn't even to say about who would be ethically responsible if, say, we did not know about the possible benefits of sickle cell anemia and were to delete the gene responsible for sickle cell anemia, and then suddenly there was a malaria outbreak in Africa. Who would be responsible for that? We would argue that we simply do not know. Furthermore, as I stated previously, my opponents would argue that CRISPR gene editing should be put out for broad therapeutic use. However, this would not even have its intended effect. If you give a kid a toy, they're going to play with it. In a similar sense, if you give Big Pharma the chance to use this really, really cheap gene editing technology, they're simply going to go where profits are largest. They're going to go towards people with big money. And where are they going to go? They're going to use it for mostly aesthetic uses. Granted, we do not say that there wouldn't be beneficial therapies produced from this. We are most likely going to see a cure for Huntington's or HeartMath if we use this technology. However, the vast majority of this money would go the way of some of the biggest technologies that big pharma medicine has to offer. Think plastic surgery, think doping medications that can be used to help people that have issues with retaining oxygen in their blood. Now, these would not be used for therapeutic purposes that we intend. They would simply go towards making more aesthetic alterations, taller bodies, bigger muscles, red hair, that sort of thing. And so we would assert that even though these technologies do have a benefit, the cost is simply too big. We simply do not know enough about this. And this isn't even to mention about who would be ethically responsible for the errors. Who would be ethically responsible for the rising inequality? As I mentioned before, these technologies would most likely go towards, say, a big billionaire who would want to fund CRISPR research for aesthetic purposes. However, if this were to happen, you would imagine, of course, that the costs of CRISPR would quickly rise, at least for therapeutic use, which would, of course, inevitably lead to these technologies being out of place or being put out of reach for the people who really need it. Plastic surgery would have great use for the person caught in a vehicle accident and got third-degree burns to their face, but if they can't afford it, they won't be able to use it. And of course, the price of plastic surgery is very high because the people who fund plastic surgery are the people who use it for rather aesthetic things, bigger boobs, fixing that scar on their face. Thus, the opposition stands firm in opposing this technology, and thank you very much for attending this debate.
So that's typically how our debates function. If you're interested, or if you like this debate, or even if you hated it and wanted to give us some feedback, feel free to come up and put in your NetID so that we can add you to the listserv and talk more about these sorts of events. So we usually do things like public debates like the one you just saw. We do things like forums where we have a question and answer session and we talk about certain issues. We also have outreach events where we go out to members of the Ithaca community and hold debates or forums with them and with the larger community, with the community at large. So if you like that, please feel free to sign up and do that. If you have questions or if you want to ask the debaters anything about this particular topic, feel free to stay behind and do that. If not, thank you guys for coming. We really enjoy that you guys came out.